Thank you very much for inviting me. And today I'm gonna present some practical and very simple, non-expensive approach to calculate the ionization potentials. And as you can see in a moment, we call the method delta MP2 SCS-IP. And the method is based on a electron propagator method in some diagonal frequency independent approximation to the second order of self-energy expression. And because it's frequency independent, it's simple single step calculations. And we combine it with spin component scale techniques. So first I will introduce the method, and then I will show how we assess the method. And we did many calculations to check how the method works, especially focusing on some benchmark sets. There are a lot of benchmark sets prepared for ionization, calculating ionization potentials, but also we did some calculations for some real systems like DNA, RNA bases, and also some photovoltaic molecules. And the work was published, so the method was published 2 years ago, and the assessment of the method was published recently in the New Journal of Physics. So work was done together with Szymon Śmiga and Sylwia Siecińska. She is a student of Szymon. The most of calculations was done by Sylwia and Szymon. And a few words about spin component scale MP2. This is well-known approach introduced by Stefan Grimm more than 15 years ago. This is kind of empirical method which should improve standard MP2. And Stefan Grimm introduced some scaling factors to the same spin and opposite spin part of the MP2 energy, and to improve the quality of the MP2 results. In the first work, he proposed coefficients, one to scale the opposite spin part with 1.2 and the same spin with 1/3, and he got these empirical parameters from some CCSD parenthesis T calculations to reproduce some reaction energies. And from this moment, so many people started using this spin component scale method, and with some success and failings. And why the method can be useful? First, it can improve the quality, sometimes up to CCSD parenthesis T, of the several or different MP type methods with scaling like n to the 4th on n to the 5th. So as you know, CCSD parenthesis T scales like n to the 7th. So, and it's very easy to implement because this is just usually just MP2 expression or approximation. And it contains one or maximum 2 parameters here, just opposite spin and same spin coefficients. So, but when we look at the method, the spin component scale MP2, not only we, but many people find then the method is very often property or problem dependent, the parametrization of the method. And in some application, it can be even system dependent. So we have to be careful when we use the original proposed by Grimm parametrization. So when you look at this table, there are several, not so many, but there are a few different parametrizations used for standard MP2, standard spin component scale MP2, and the original one is here, and the second one is also very interesting because Head Gordon proposed a method where he can scale only the opposite spin part of the MP2 energy. So this is important because in that case, the cost of calculating this SOS in this case, MP2 is like its case like n to the fourth. So we work with this spin resolved MP2 type methods for already 8 or 7 years, and we use it for several approaches. First, we use the spin component scale methods to somehow define or fix the problems with orbital dependent functionals. I have no time to talk about this, but using the spin component scale methods approach to defining the orbital dependent functionals, correlation functionals, we can fix some Gerling-Levy problems like overestimating and convergence problems, but I'm not going to talk about this much. But the second approach was to calculate interaction energies and dissociation energy curves for non-covalently interacting systems. And our motivation was actually this table, very strange behavior of the parametrization of the spin component scaled MP2 method. So as you can see, this is the most popular parametrization for calculating the interaction energies for non-covalently interacting systems, and it was proposed by Head-Gordon group. And as you can see, it's quite opposite to the standard one. Actually, the standard one parametrization, the original one, does not work for this non-covalently interacting systems. But there are several parametrizations and they are very strange. So we look at the problem and we have found that the parametrization in that case is really system dependent. So there is almost no way to find some universal set of parameters to calculate with this spin component scaled MP2 interaction energies for non-covalently interacting system. But we have found something interesting and we use it to fix the system dependent parameter in the calculation with the spin component scaled method. So the idea was very simple. At some point here, when we want to calculate the curve, we fix the coefficient to obtain the results of the quality of CCSD parenthesis T. For example, if you want to scale only the opposite spin part of the MP2 energy, we can calculate this coefficient here. So we do it at some distance, here, and then the rest of the curve we can calculate using this fixed coefficient and simple MP2 energies opposite spin calculated from the opposite spin part of the MP2. So it scales like n to the fourth. So as you can see, the coefficients, we check the method for a few systems and the coefficients are really system dependent. So they vary from, some of them are bigger than 3 and some are like 1.2. So how the method works for this, so there are some binding energies for the standard system, helium to neon to, and the curves are they are similar for all the systems. So what we can see, the CCSD parenthesis T results, it's the solid black line, it's our reference. So our results, as you can see, maybe you cannot, but they are exactly, almost exactly on the CCSD parenthesis T, and they are calculated with scaled opposite spin part of the MP2 energy. And this is for helium to neon is very similar. Here you can compare with the MP2, the standard for non-covalently interacting system parametrization proposed by Head-Gordon in this case, and that case gives even worse results than the standard MP2. So what about the bigger systems? And this is, for example, benzene dimer. So the crosses are the CCSD parenthesis T results, and our results of our calculations are exactly here. So, and this is benzene HCN, similar behavior. So the methods work very well. Actually, the advantage of the method is, so we calculate the whole curve with the cost of n to the fourth, quality of CCSD parenthesis T, but at one point we have to fix the coefficient and we have to do the expensive CCSD parenthesis T calculation. So, okay, I'm moving to the main point of our talk, of my talk. But before that, I want to advertise also our another approach to spin resolved MP2. So we did some density basis analysis of spin resolved MP2 method, and I'm not going to show it, but we have found well-defined proportionality of the same and opposite spin parts of the correlated electronic density, not just one number like in the case of energy, but here we have found the proportionality of the whole correlated electronic density, and also the parts of same and opposite spin parts. But also we were able to reproduce CCSD parenthesis T density from just opposite spin part of MP2 correlated density. And it was published two years ago. Okay, let's move on to the main subject. I'm going to show how to calculate the ionization energies using the spin component scale delta MP2 procedure. So as I mentioned before, the method is a single-step procedure and it's based on the electron propagator method with diagonal frequency independent approximation to the second order of self-energy. And it's combined with spin component scale technique. So when we calculate the ionization potentials, we can use several types of methods, classes of methods. The one is the methods which kind of SCF type methods like Hartree-Fock or Constant DFT, when we can directly take the orbital energies and use it as a first approximation to the negative ionization potential. And for Hartree-Fock or even for Constant DFT, the approximation is very bad. In standard Constant DFT, the error is usually few electron volts, except the method, the CAM QTP functionals developed by Bartlett. You can see results later. The other method is the very effective energy different method. We call it delta dash method, delta dash MP2, delta dash DFT or CCSD. So the ionization potentials are calculated as a difference between total energies of n minus 1 electron systems obtained with a given method. So it's a powerful method. It includes orbital relaxation and can be systematically improved. But of course, it's expensive, especially when we go to the CCSD. For example, here it's case like n to the 6. And there are also two state-of-the-art techniques or approach, very popular. One is for calculating the ionization potential, one is the equation of motion couplet cluster method. Very powerful, but well-defined, but expensive. And the methods which are known for so many years, the electron many-body green functions or electron propagator methods. And because our method is it's a modification of this one, I will say just a few words about this electron propagator method for calculating the ionization potential. So in the electron propagator theory, the binding energies can be obtained from the self-consistent solution of one electron Dyson equation with some energy-dependent correlation potential, which is called self-energy. Here is the self-energy potential or operator. And the form of this operator is usually expressed by perturbation theory, and at the simplest approximation of the second order with some diagonal approximation, it defines the method which people call electron propagator second order EP2 method. But if you want to avoid the self-consistent solution of the Dyson equation, we can calculate the value of the self-energy for in a single-step calculation after Hartree-Fock, fixing the Hartree-Fock orbital energy by this the self-energy correction calculated for a given orbital energy. This procedure is equivalent to the delta MP2 method, which, in contrast to delta dash MP2, is an energy difference between n-1 electron system, but all quantities were calculated for the n electron system. Okay, so in general, the accuracy of the second order methods, they are not really good. They overestimate the ionization energies. So from 70s in this the previous century, people have to go to the higher orders, and they propose some methods like outer valence Green's function theory, or P3 or P3 plus methods. You know, the names Sederbaum, Lindenberg, Zakrzewski, and especially Ortiz is still working in this area. The problem is the cost of the second order method, this case like n to the third. I'm talking about just cost of the method after the Hartree-Fock. And the third order method scales like n to the fifth. So the question is, can we somehow use the spin component scale idea to modify the delta MP2 method to improve the quality without increasing the cost? So the method which we propose, we call it delta MP2 SCS. So it's a very simple single-step calculation based on this formula. So we do Hartree-Fock, and then we calculate the second the value of the self-energy for the given orbital energy. But we propose to scale, like in the spin component scaled MP2 method, scale the same spin and opposite spin parts of the self-energy. As you can see, the expression for the second order self-energy approximation is they are similar to standard MP2. That's important because then it's easy to implement them. So if we want to somehow to make the method working, we have to say something about the coefficients. So we check it for a few systems first, and we have found that there is the way to find some universal parametrization for in that case. So we choose the training set of 50 molecules, which is a subset of some bigger benchmark proposed by McKinney, Coe, and Cole 5 years ago. Most of all the calculations were carried in augmented CCP-VTZ basis set. So to fix the coefficients, that we analyze the error of the HOMO IP calculated with our delta MP2 SCS with respect to delta dash CCSD parenthesis T, and also with respect to experimental IPs for the whole benchmark set as a function of the coefficient. So what are the benchmark? So results are here, so of our scan. So what we have here, so the minimum error is it's in a black color. So as you can see, the standard delta MP2 is somewhere here with the error about 1 electronvolt. The standard parametrization proposed by Grimm or Head-Gordon is somewhere here, but were able to find the set of parameters which can minimize our error. Okay, the values are actually here. So they define our method. Very simple. The coefficients are, of course, empirical. And we have two options. One, we can scale same spin and opposite spin parts. And here we can scale only the opposite spin part. As I said, it's empirical. As you can see, the coefficients are less than 1, so we can fix the overestimation of the delta MP2 method. So the assessment of the method. So first we check it for few benchmarks. First was the benchmark full set of 100 molecules, and as you can see, the error of the delta MP2 method, which we propose with the coefficients, it's very nice, and it's only slightly bigger than the error of IP-EON. And we fix this number. This is delta MP2 standard, and with the parametrization we fix this number, and we are very close to the much more expensive third order calculation. But we check how it works with respect to experimental data for this benchmark set. So as you can see, our reference delta-CCSD, the error is also very small and similar to IP-EOM, and our results are pretty good also with respect to experiment. So we check how our method depends, the parametrization depends on the choice of the basis set, because we optimize the parameters here for triple zeta. So as you can see, it's very stable as you compare to other spin component scaled approaches. We also did some estimation of complete basis set at complete basis set limit. And again, as you can see here, the errors are really small and stable. So we move on to some bigger or different benchmarks. First, 24 organic acceptor molecules. So you can see them here. I don't know the names. And how the method works? Again, and the error was calculated with respect to delta CCSD parenthesis T CBS data. So as you can see, the parametrization works even in that case and provide results much better than maybe not much better, but better than the third order approaches. And we also fix this. This I can skip. And the next benchmark, we use the benchmark provided by Bartlett, and it was introduced by Bartlett to check his CAM QTP functionals, DFT functionals, which were developed especially to reproduce ionization potentials. So as you can see, the standard DFT, the error is more than 1 electronvolt, sometimes 3 or 5 electronvolts. And the Bartlett's Bartlett's functionals looks very nice, and we check how our simple method will work, the parametrization work for these systems. So for calculate the HOMO IPs, the errors are very nice. We are better than CAM QTP and better than the third order methods. And when we use our parametrization, our method to calculate all IPs for this benchmark 155 molecules, errors are slightly bigger, but they are still better than CAM-QTP, and in most cases better than the third order approaches, except this P3, which is in that case a little bit better. So, but in this case, we fix much bigger error of delta MP2. Okay, and just few more examples, not too many. We move on to some examples of some real, not real, but bigger systems, some DNA, RNA nucleobases like guanine, adenine, cytosine, and so more. The knowledge about IPs is important because people want to understand the electrostatic interaction of the systems with other molecules. So results are here, and again the error. So here we calculated the not only first IP but first two virtual ionization potentials. So again, this method, even it's as I said, it's empirical parametrization, works remarkably well. So as compared to much more expensive third order methods, and in that case, error was calculated with respect to equation of motion, CCSD calculation. And we also look at for some large photovoltaic molecules, which are important for some solar cells, and you know, the names are here. I know C70 or C60, but the other I cannot even pronounce. So again, results are here for this system, and they are calculated with respect to experiment. And as you can see, our methods behaves very nice. So it's as previously. So it's in that case, the outer valence mean function works a little bit better than our approach. So the single example, it's a calculation of IPs for single wall carbon nanotubes. This C20, oh, the C20, H20, and here it can be 40 up to 200. So we did the calculations and compared the IPs. So the error of IP was calculated with respect to IPOM, but only up to C80, because we couldn't run the IPEOM for higher systems. We simply used the numbers from the publication, different publication. So as you can see, again, very nice behavior, even for such a big systems. So these are the conclusions. So we proposed some new parametrization of spin-resolved delta MP2 for calculation ionization potential. And as I said, the method is very practical, accurate, and what is important, cost and implementation free, because to implement it, you simply have to program or use the expression for the self-energy at the second order, which are almost exactly the same like the standard MP2. And what is important, this is just single-step calculation based on the Hartley-Fock reference and does not involve any diagonalization, self-consistent solution, except, of course, this Hartley-Fock. And the quality of the highest occupied IPs, but also for all IPs which we check, is almost IP EOMCC SD quality. And the scaling of the method after post-Hartley-Fock is just n to the third. Okay, thank you very much.
Let us thank the speaker. And are there questions? Anybody has a question? If not, I ask a short one. Does this method in principle work also for molecules with a triplet ground state? It would probably require different spin scaling coefficients.
That I'm not sure. So we didn't check such a systems. We are working on that, and I cannot answer. So we hope yes, but you know it can be some spin contamination problem. This is
yes, exactly.
much more difficult problem. So it's
okay. So thank you.